Okay, so as you mentioned, so today we are going to talk on the topic of the solvent-reduced electrode manufacturing, also from the both sides, let's say, innovations in anode and the cathode processing. In the beginning, I will just say a few words about the Fraunhofer IKTS. So Fraunhofer IKTS is located in the Dresden. It's the core of the institute. It's in the ceramic technologies and the systems. It's around about 800 employees, mainly scientific and technical and administrative staff, and around about 100 PhD or diploma students. The overall budget is 90 million, and the industrial revenue from the project, it's around about, let's say, 30% of the overall budget. About the Fraunhofer IKTS system, IKTS, there are several sites through the Germany. It's, let's say, 3 located in Dresden, and then another, it's about 30 kilometers, it's Freiberg, where also my group is located and where we do the activities on the electrode manufacturing. And then there is another one in Helmsdorf. Also, they are working on different topics there. Let's say there are a lot of groups that are involved and working on the field of the battery. So there are a lot of competences at our institute. So starting from the powder development, then powder synthesis, process development that we are doing on my group. So we are working on the solid state battery, and I would say in most of the chemistries. Then everything we do also in a lab scale up to the pilot lines, a lot of electrochemistry testing. Then we do the recycling, sensor development for the inline monitoring, a lot on the cell design, non-destructive testing, and in the end also a lot on the topic of the battery intelligence and trying to, let's say, to develop also real-time feedback loop on the whole process chain in the battery. The group that I'm leading, it's process development and monitoring. So usually what we are doing, so we have a different kind of, let's say, mixing techniques. So we are starting from the state-of-the-art mixing, coating, drying, and calendering. We do also cold, hot plastic film extrusion. All the processes that we are working, usually we can do everything from the lab scale up to the pilot line. We have in our facility a dry room environment with a dew point -60. We do the upscale up to the technology transfer to the industry, and then a lot on the inline monitoring of the processes, then data analysis, correlation, and the modeling. On the battery intelligence, so we do in our coating line, a lot of, let's say, inline monitoring systems are integrated. So then we are acquiring a lot of data, and then we use all the data somehow to make, let's say, kind of to predict also the coating uniformity, thickness, active material distribution, and in another way, somehow to make the feedback loop when we have, let's say, problems during the processes. This is our coating line. This is a tape casting line. So during the whole process, starting from the, let's say, the mixing, we could check inline the slurry or the quality of the slurry, the viscosity. Then we check the wet film thickness and age accuracy. Then we have eddy current sensors where we track and check the drying condition and the residual moisture. Then in the end, to see or to detect the defects on the electrode surface, such as agglomerates or line defects or impurities. We have a combination of laser speckle and photometry, and then all this is in a automatic way, and also we get the feedback when let's say something is going on the wrong direction. I think this would be the last slide about the, let's say, tape casting and other topics that we are doing here. So as I mentioned, we are working a lot on the electrode design via multi-layer systems with free, let's say, fluorine binder systems. Then we do a lot on the investigation of the different water-based binders for lithium-ion batteries. And then we work also in other chemistries such as aluminum-ion battery. As you can see here, it's a double-side coated cathode, which is going to aluminum-ion batteries. Now we would start on the topic that is for today. So on the really solvent-reduced manufacturing. So what was the motivation behind? So as we all know, on the tape casting or on a wet coating technology, there is a lot of solvent which is used. First of all, the solvent which is used is NMP, which we all know is toxic. And in another hand, all the solvents need to be dry to recover, which is a lot of cost. Usually around about 40% from the cost on the cell is coming from the electrode production, mainly because of the drying energy which is needed to dry the electrode. Therefore, we developed the semi-dry extrusion process, so where we can really increase the solid content. So we reduce the need for the solvent, which means we reduce also the drying energy to dry the electrode. With that, it means that we would save around about 30% of the solvents. And another point is that nowadays there is a lot going on the completely dry technology, but here is the, let's say, one of the advantage of the semi-dry extrusion process, that we are still flexible on the binder selection, where on the dry technology, we are only limited on the PTFE because you need to fibrillate the binder in order to make the network on the electrode. But here we are still flexible since we have still a bit of solvent on our, let's say, active materials with the binder. With this process, also we could achieve higher film thickness on the electrode. So we could 120 to 400 thick electrodes, and all the electrodes after the coating are on the porosity 40 to 50. We could process different kinds of nanomaterials without agglomerates, and as well direct extrusion. It's a good approach also on the other chemistry in solid state, sulfides, polymer oxides, hybrids. Here we could just see some of the, let's say, components that could be manufactured using the semi-dry extrusion process. So we could process a lot, or we skate a lot on the sulfide components for the casting of the thin electrolytes, and then also for the process development on the polymer electrolytes. So both, let's say, this kind of electrolytes could be manufactured using the same technology. So the whole flexible extrusion and coating line, this is how it looks at our, let's say, facilities. So it's twin screw extruder there, where we have the dosing and the mixing. Then we have the slot die, which is used for the film forming. Then we have a step which is called smoothing step. Then we do the drying, and then is the winding, and then after that is the calendaring. So about the each step, so the twin screw extruder which we are using, so there are, let's say, different possibilities where you want to do the dosing of the active material, the binder, and the solvent. So through the whole twin screw, there are 4 positions where you can dose the, let's say, in the first position just the powders, and the second position the binder, and then this could be optimized depending on the chemistry that you are using, and also depending on the process that you want to develop. The slot die that we are using, it's a 100 millimeters width. Also, we have 150. The slot die geometry, it's one of the key points in order to achieve really flat film and also to make this direct extrusion of the material to the current collector. On the bottom, you can see the pictures, how that looks for the anode and the cathode, directly coating of the film to the current collector. To see it more, so as we mentioned, it's a continuous, let's say, mixing or a continuous process. So here you can see we are doing the dosing of the powders, or let's say of the active material, usually depending on the project, could be NCM, LFP from the anode side, the graphite, or also silicon oxides together with the graphite. After we do the first dosing of the active material, then we start with the dosing of the binder or the solvents. And then on the second step, you can see how it's done, the direct coating onto the current collector. So you can see that the film is well, let's say, homogenized and plastified in order to have also a good adhesion to the current collector. On this process, at the moment, we are using mylar film, which is necessary due to the process of the smoothing. So on this smoothing process from the slot die, when the let's say the material is going to the current collector, and then between two rollers to do the smoothing, you need in the upper roller to have a film which it protects the active material to not be sticky on the roller of the, let's say, of the calendaring. And that's why we use a mylar film. And also this is a process which needs to be optimized in order to not have a material which is still sticking on the mylar film. But we are also working on this step. So in the future, the plan is to be also ahead of this step. So trying to find other solutions, so to not use any film on this step. And the last step is where we do the drying, and then is the winding, and then let's say we do the calendaring of the electrodes. Here we are just highlighting, let's say, some let's say feature from the semi-dry extrusion. So as I mentioned, the solvent, it's really minimal that we are using. The binder, so as I said, we could use different binder systems, water-based, PFADF, so we are not limited on the binder. Then the mixing method here, it's a high viscosity kneading extrusion. So during the extrusion, it's a kneading, let's say, mixing method. And then the film or the forming method of the electrode, it's through a slot die. Drying, as I mentioned, it's, I would say, minimal, since the solid content is really high. And then the coating thickness control, it's high, since we are using a slot die, which is also used on the tape casting method. And we are able to have a really wide range of the aerial capacity which we could produce on the electrode, which is not the case when we are doing on the tape casting, since there, when you are doing really, let's say, high aerial capacity electrodes, there you have a lot of cracks, since the film of the electrode, it's, I would say, really thick. Then the electrode integrity, it's really high with really improved mechanical strength, and the scalability, it's higher scalability with continuous process. Also another advantage from the tape casting, where it's a batch process. And then the energy and the cost efficiency is high due to the minimal drying and reduced solvent handling. As well, on the right side, you can see also double side coating. So we do first one side, and then we do, after the winding and drying, we do the other side coating. Of course, could be done in the future also both sides simultaneously, but this means that you need to have two extrusion and also two slot dies, so everything should be doubled before, let's say, the drying step. Here, just an example of the analysis and validation in a cell. Here we used, let's say, as the active material was NCM 622, and we did with and without carbon nanotubes. So here, also in this case, we were presenting, let's say, 5 milliampere per square centimeter and 10 milliampere. So here we can see that the extruded electrodes also at 10 milliampere per square centimeter has still a good, let's say, specific discharge capacity. And it means that it's still, let's say, in a good, let's say, running, especially when we have a low C rate. For energy storage, this could be a really, I would say, a good approach. And what we observed is that just adding a few, let's say, content of carbon nanotubes improves not only, let's say, the specific discharge capacity, but also the electrode flexibility and mechanical properties from the electrode. We all know that when the wet coating technology is used, there are usually a lot of problems on the migration of the binder due to the drying. Since there is the drying, let's say a fast drying process, and then usually the binder intend to go to the, let's say, surface of the electrode, and then it's not well distributed through the whole, let's say, area of the electrode. In this case, we compared, let's say, two electrodes, one from the tape casting and one from the process of semi-dry extrusion. And as you can see, in this case was a PFADF binder. You can see how well it's the distribution of the binder on the process of the extrusion, since there is really low solvent amount, and that's why during the drying there is no binder migration comparing on the wet coating process. As well, on the right side, you can see, let's say, extrusion and let's say the tape casting over 500 cycles. So we can just, this was to confirm that the extruded electrodes, let's say, can run also on a really long cycling life. What I would say as the advantages, so as I said, we could go really to high capacity electrodes, and also the speed as well. It has, let's say, low energy consumption on the drying, the scalability, so easy to scale up, and it has still tight thickness control comparing, for example, in the case of dry technology, where still the film thickness control, it's a challenge, but here not, since we are using still a slot die. The quality, it's still uniform layer during the whole width of the slot die. The benefits, so we are using really minimal solvent, and then it's, I would say, faster processing, also reduced operating expenses, so which means that also the let's say the cost investments is not that high comparing to the tape casting. Since in this case it's not necessary to have all, let's say, the drying and the recovery of a lot of amounts of the NMP. The challenges, of course, let's say for each kind of chemistry, still needs to be the slot die somehow tuned due to the differentiation on the paste rheology, since different chemistry, different binder has also different kind of behavior on the property of the viscosity. That's why it's necessary the slot die to be verified and check the geometry of the slot die if it's compatible with the material that it's going to be extruded. Handling of the protective film in the smoothing process, as I mentioned, it's a step which is also need, let's say, a lot of optimization. But as I mentioned, we are going forward on that topic, and soon we will have another way how to handle that. Application, so as I said, could be in a really high energy cell, so thick cathode for EVs, and also storage, and also could be really, I would say, also another advantage comparing with the completely dry technology is that there we need, let's say, from the beginning, or a lot of adaptation cannot be handled or taken from the current, let's say, processes that the industry is using, because it's a bit more different process. But in this case, we could still use let's say, the drying channels, the roll-to-roll system, and just adapt the step before the drying, and using not a batch mixing as it's used in tape casting, but we just use an extrusion process. We, let's say, with a slot die, and then we are able to make let's say, a direct coating, and then we use the whole, let's say, other part which is already, let's say, installed on the other in the industry. As the conclusion, so I would say the semi-dry extrusion process bridges the gap between, let's say, the scalability, sustainability, and the performance, with really minimal solvent use, saving more than 30%, and then having also the compatibility to do also thick electrodes. It offers, I would say, a lot of, let's say, advantages as alternative to the traditional slurry coating and also dry coating, which, let's say, somehow it's making also the bridge between them. Also, its approach for the next generation battery manufacturing, and I would say it's a good step toward the cleaner and also sustainability process chain in the whole, let's say, battery manufacturing processes. So just to make, let's say, a view on that. So as we said, we have the mixing, then the slot die, coating and smoothing, drying, and then the electrode. So we would have a really floor space reduction, because less, let's say, needed the drying channel in this case, solvent reduction, capex saving, lower energy consumption for the drying. But at the moment, the level of industrialization is not that high, but there are a lot of projects that they are ongoing on this direction, and soon we will have also a scale, let's say, a higher scale up on this process. Thank you for your attention.